So welcome back, and I had requested you to give me the outputs or to confirm the outputs that we have here. But before I go to that JK, there's two combinations which I didn't do for the RS flip-flop, and those two combinations are the one where we have 1-1. So we'll check for the RS flip-flop, it's important, but for the other flip-flops, this 1-1 is not important. So I would want us to have a look at what happens when you have a 1 at this point and a 1 at that point. Please note that we said when you have a 1 to the input of an OR gate, always we know that the output will be 0. But if we start with the first one, we will get this to be 0, but this will be 1. But what about a case where you start with this one? If I start with this one, then this will be 0, and this will be 1. So can you see what's going to happen? These two guys will be fighting. I want to be 0, I want to be 1. I want to be 0, I want to be 1. And that's why we have racing. This racing condition is where we have change of state 0, 1, 0, 1, 0, 1, uncontrollably. So it's a condition that we usually have in the RS flip-flop, but the other flip-flops don't have it. The condition where we have S is 1 and R is 1. Because we know that this is supposed to be a 0 output, and therefore when this is 0, this is 1. And we also know that if we have a 1 here, this is supposed to be 0, and this is 1. You realize that the two states would want to be actually the output. So that leads to a situation where we'll be changing state from 0 to 1, 0 to 1 throughout, and that becomes what we call racing. It's also called an invalid state. It's also called an unstable state. So I'd forgotten to indicate that. So it works the same for the clocked RS flip-flop. So let me now move to the JK. We see what you guys have, whether you manage to do something. And if you really manage to get something there, then that can be very good. We actually managed to get the outputs correctly. That can be good. So we're taking the first step. This time, we're also picking the inputs. Before, maybe I go to the combinations we have here. You guys, you realize that the RS flip-flop is here at this point. So this is our R, and this will be our S. Now, we've already discussed about how this works. So if you have these two inputs, always you will be able to tell what you have at Q and Q bar. But that has to come from these inputs we have here, which are called the J and K. The clock will always be assumed to be 1. And if you look at the difference between this and the RS flip-flop, is that we have just added an AND gate here, another AND gate here. In fact, if you look at the clocked RS flip-flop, they're the same. The only difference is that we're having 3 inputs here and 3 inputs here. But the RS flip-flop, which is clocked, we just had 2 inputs, the clock here, and then we had an R here, and then we had an S here. So the additional feature we have to this is if you look at the clocked RS, it does not have this line. And if you look at this one, it does not have this line. Please know that those two lines are very important in these memory elements. Why? Because they are feedback and they are the ones which enable us to have storage in a device. Feedback is actually what makes storage in our solid state devices, storage devices. Remember, you talked about solid state hard disks. You've talked about flash disks. All of them are developed using the RS flip-flop as the most basic device. Actually, a flip-flop is the most basic device of memory or memory elements. So what you're talking about here is basically the structure where memory starts from. The RS flip-flop, the JK flip-flop, the D flip-flop, and the T flip-flop. So now, let's take the combinations. Q is 0. The first combination is basically 0 here. So you can see that. Q, that's what we have here. And if Q is 0, what is down here? 1. Now, if you have 0 here, what comes here?
Zero.
Yeah, because you are feeding it back and you expect it to be 0. So if you have a 1 here, what do you expect to have here?
1.
1, that's correct. And we are being told the clock is always 1. So you're being told that K here is 0 and J is 0. So we put 0 here and you also put 0 there. So the question is, what are we going to have here and what do we have here and what do we expect to have here? So if you did it, you can be able to tell me what we have here.
0.
Yeah, 0 and 1 is 0. Please note that anytime you have a 0 at the input of an AND gate, the output is always 0. So 1 and 0 and 1?
0.
0.
So correctly, that is 0. Now, 0, 0 means what for RS? Remember what you did for the RS?
No change.
No change. So this time we don't put no change. We put a 0 because we have it. We know that Q is 0. So we actually put 0 here. Reason? Because we already know it's a 0 at the output. So we don't put no change. We actually put 0 because we are seeing it here. Now let's look at the next combination.
So for this case,
Yes.
quick question. For this case, Q will always be given before we found out Q bar or
That's
the
correct.
values of RS.
That's very correct. Q is always given and it's here. This is the line for Q. That column.
Okay.
So for these first 4 combinations, Q will always be 0. What you're not going to know is the K and J. So let's change. We go to the next one, and our next one here is K is 0. K is 1, sorry. Let's see what happens when you change K to 1. So we put 1 here. 0 and 1 and 1?
0.
0. 1 and 0 and 1 remain 0. So no change again. We put 0 here. That's actually what we have at the output, which is 0. Why? Because it is 0, we know it is, and there's no change. But now, let's change our K to 0 and J to 1 and see what happens. This is 1 and this is 0. So 0 and 0 and 1?
0.
0, that's correct. 1 and 1 and 1?
1.
Yeah, 1 and 1 and 1 is 1. So you put a 1 here. Now, remember, S is 1, R is 0. What did we say would be here?
Set.
It will be set. Please note that it's set, which means the 0 that we had here we started with will change to what? It will change
1.
to 1. And that's why you can see a 1 here. And I hope all of us are now okay with actually what you have done at that point. When you change A to 1, this will be 1 and 1 and 1. The output's 1. S is 1. And if S is 1, we said the device will be set, which means if it was a 0, it changes to 1. If it's a 1, it remains 1. So let's look at the next one, where we are having our K is 1 now again. So K changes to 1 once more. And 0 and 1 and 1.
0.
0.
So 0 and 1 is 0. 1 and 1 and 1 is
1.
1. So S is 1. What does that mean?
1.
Q will be 1, which means set. And that's what we have here. So let's look at the next one. I would want somebody to take me through the stages one by one. When we have Q is 1, somebody can do that for us. When Q is 1, we put here to be 1. And this changes to 0, so this will change. J, K will change, most probably, in the RS. So let me clear everything from there. And then so this is 1 now. Down here we expect to be 0 definitely. So we feed back a 1 here. What is down here? 0. Now let's have J, K. J, K. J is 0. K is 0. That's what we have at this point. So please take me through. What do you have here?
0.
So this will be 0. What about this one?
0.
0. When R is 0, S is 0, what do you expect?
No change.
No change. But what's our no change?
1.
It's 1. So this is 1. Now, what happens when you change your K to 1? Let's change K to 1 here. So tell me what you expect.
1.
So at this point we have 1. 1 and 0 remain 0. So R is 1, S is 0. Output we expect?
0.
The output will be 0. Why do you think it's a 0?
That's why it said
It's a reset. When R is 1, we have reset. So the output will be reset. And therefore, that's why we have a 0 at this point. So the second last one is where we change J to 1 and K to 0. So J is 1 and our K is 0. So J is 1. So 1 and 0 and 1?
0.
0 output, that's correct. 1 and 1 and 0?
0.
0. R is 0, S is 0. What do you expect? What do you expect?
No change.
No change means what?
1.
1. That's why we have a 1 here. And the last combination is where we take now k to be 1. So if our k is 1 here, so 1 and 1 and 1,
1.
this changes to 1. 1 and 1 and 0, 0. R is 1, S is 0. What do you expect to be the output?
Reset.
Reset, and if it's reset, we have a 0. Just know that that's how that device works. And that's one of the most complex devices that we can discuss about, the JK flip-flop. Coming up with this output is not that very easy, as you have noted. But I believe for those guys who understood what we had for the RS flip-flop, you're actually able to get something. Yeah. That's our JK flip-flop. So just look at the difference between the JK and the RS, clocked RS. You realize that the difference is only in the feedback. There's a line that comes from here, it joins here. There's a line that comes from here, joins here. That's the only difference between this device and the JK that we are seeing here. Let's look at the next flip-flop, which is the D flip-flop, and that's what we have here. You can see it has one input, two outputs, and the diagram looks like this, logic diagram. Can somebody tell me the difference between the JK and the D flip-flop? It's a very clear difference, very simple one.
The inverter.
Please note that this one, K and J are looped like this, but through the K input we have an inverter. That's the difference between a JK and a D flip-flop. Now let's go through the input. We are given Q, we are also given D, because it has just one input, which is D, and the other feedback input. That's what we combine together. So let's check what happens when we change. When this is 0, definitely this will be 1. We feed back this one. And we also feed back a 1 there. Please note that the clock is always 1. Now, the first combination, Q is 0, D is 0. This one here. What do you expect here?
1.
1, that's correct. What do you expect down here?
0.
0.
So 0, 1, 1. What do you expect here?
0.
That's correct. 1, 0, 1. What do you expect here?
0.
0.
0, that's correct. Remember, these are and this is S. R is 0, S is 0. What did we say is supposed to be the output?
No change.
No change. We already have a 0, it remains 0. So let's change D to 1 and see what happens. So this is 1. So if this is 1, then this is what?
0.
0, that's correct. So then this is 1. 0 and 0 and 1?
0.
0. 1 and 1 and 1?
1.
So 1 and 1 and 1 is 1. Therefore, we change this to 1. S is 1, R is 0. What do you expect?
Set.
Set. That's why we have a 1 here. Always when S is 1, R is 0, set. When R is 1, S is 0, reset. So let's look at the next other combinations, and you realize that we change this now to 1, Q will be 1, and therefore what you are feeding back there is so this is 0, sorry, this is 1, and definitely this will be 0. So we are going to have a few changes here. So we have Q is 1, so it fits back. You have a 1 there, and you have a 0 here. D is 0, so you put a 0 here. What do you expect here?
1.
1, that's correct. Then this remains 0, so 1 and 1 and 1.
1.
1 and 0 and 0.
0.
R is 1, S is 0.
Reset.
Reset, and that's what you are seeing down here. What happens when you change your D to 1? So this changes to what?
0.
To 0. And 1 and 0 and 1?
0.
0.
0. 1 and 0?
0.
0.
0 and 0?
No change.
No change, because we already have a 1 here, it remains 1. Please note that the D flip-flop from this diagram here transfers the input to the output. If the input here is 1, then the output will be 1. If the input here is 0, what will be the output?
1.
We said this device, if you give it a 1 input, it transfers to output. If you give it a 0, transfer to output. If this is 1, this will be 1. If this is 0, this will be 0. Please note that. Look at this. D is 0, moves to the output. D is 1, moves to the output. D is 0, output. D is 1, moves to the output. So it basically transfers our input to the output. That's what this kind of device does for us, and is the most commonly used in the development of registers. So that's all about the D flip-flop. The last one, which is also similar to this one we have discussed, is the T flip-flop. So let's have a look at it also. And it's called toggle flip-flop. It changes state. It also has one input, two outputs, like this, when you don't include the clock. Can you tell me the difference between this and the D flip-flop? The difference between the T flip-flop and the D flip-flop?
They have the same input, T.
That's the same. That's a similarity. I want a difference between this and the D flip-flop.
The input at K is not inverted.
This is a T flip-flop. The first one, the one we just looked at, is the D flip-flop. I want you guys to give me the difference between the two. Just look at the two devices. You can hear a small difference. Just look at that one and look at the next one.
K is not inverted.
Please know that
There's no inverter in that.
there is an inverter here. Down here, there is no inverter. So the connection for the T flip-flop is that we just take the JK flip-flop and we loop it. So if you look at our JK flip-flop is here, just take this one and then loop it, connect it down here. That gives you the T flip-flop. As simple as that. So let's have a look at how it operates. So we compare the truth table here. It's also similar to what we've just talked about. In fact, the operation is very similar. There will just be a slight difference. This is 0. This is 1. That's when you take Q is 0. Then you feed it back. 0 is fed back here. And we have a 1 here. And then if we put T to be 0, we say the clock is always 1. So what do you expect? 0 and 0 and 1. What's here?
0.
0. Then 1 and 0 and 1.
0.
0, 0 to RS.
No change.
No change. So what do you expect at the output?
0.
Because there's no change, we say it remains 0. That's what we have here. What happens if we change T to 1? So 0 and 1 and 1, 0.
0.
1 and 1 and 1,
1.
1. When S is 1,
Set.
we set. So if it's set, it changes to 1. That's what we have here. So now we change that very fast to 1, and we will see what happens. So I have a 1 here. So that will be 0. And this is 0. Because we are dealing with this case now, this one. So we feed back a 1 and we feed back a 0 here. So since T is 0, we're going to have 1 and 0 and 1.
0.
0, that's correct. 1 and 0 and 0.
0.
0.
0, that's correct. 0, 0 for RS.
No change.
No change. Because you already have a 1, it remains 1 here. And the last combination of 1, 1 is given, we change T to 1. This is 1. So 1 and 1 and 1.
1.
It should be 1. So 1 and 0 and 0.
0.
No, it's actually 1 and 1 and 0.
0.
Still remains 0. So R is 1, S is 0. When R is 1, what
Reset. Reset.
reset. And if we reset, you can see we have a 0 at the output. And you can see the operation is quite similar to the one that we have just talked about. Please note that this device changes state when the input is 1. When T is 1, in the next clock, it will change to 1. If it was, if the output here was 0 and T is 1, then it changes to 1. If the output here was 1 and this is 1, then it changes to 0. So it changes state when you have a clock variation. That's what you call a toggle flip-flop. We've done the 4 flip-flops. That's how they are supposed to be. And please remember, our flip-flops are the basic elements in memory. They are the ones which make memory. That flash disk that you walk around with, inside are very many flip-flops. In fact, millions and millions of them. Depending on the number of bits it can be able to store. So these flip-flops are the ones which are again used to develop registers, and they're the ones which you use to develop counters. Where do we apply counters? You guys, state machines. The devices out there that give you the vending machines. They usually give you products. Maybe if you want to buy something and it's automated, they actually use what we call state machines, and the flip-flops are the ones which are used to develop them. So you can see they have very many applications, including the registers and the counters that we are going to talk about. And that's what comes next. Though I think there's something I want to look at here. I just want to look at the state diagram for only the D flip-flop. The others, I think you can just look at them and see what happens. If you looked at our table for the T flip-flop, we had Qn was at n plus 1 was at the output, D was here. So we have interchanged them. If I want to move from 0 to 0, what should I have at the input of D? If I want an output of 0, what do I expect to put at the input?
0.
Please remember I said, if you want a 0 output in a D flip-flop, then input a 0 input. If you want a 1 output, then input a 1. So like now, Qn plus 1 is 1, then D should be 1. The same case here, when we have 0, D should be 0. When you have 1 here, D should be 1. So sometimes this is not very important. We're just looking at the output. But usually call it a state diagram or transition diagram and a table. So if I want to move from 0 to 0 like this, then D should be 0. That's what you're looking at here. If I want to move from 0 to 1, then D should be 1. If I want to move from 1 to 1, then D should be 1 again. That's what we are picking what we have here. Then 1 to 0, then D should be 0. These diagrams are usually important in designing of the counters. And I've just looked at this one because at some point I would want to design for you a counter using the D flip-flops. And we're going to use this table or this diagram. But the rest are just similar and they are simple as what I've indicated there. So the next one is about registers. This one is a very simple section. I think it will take a very short time to go through. And registers are devices which store data. You had registers from time immemorial, even in primary. You used to have registers. So they store information. They're developed using flip-flops. At this time, I indicate that D flip-flops are commonly used. So they sometimes have a common clock or they can have different clocks, but most of the time they deal with one common clock. Types of registers. This is very simple. They are serial input, serial output, which means one input, one output. Serial input, parallel output. What does that mean?
One input, several.
Yeah, one input, several outputs. That's correct. Parallel input, serial output.
Several inputs, one output.
Yeah, many inputs, one output. Then parallel input, parallel output means many inputs, many outputs. Then we have shift registers. which are also common, and remember they are used in binary operations. There are two types of shift registers. We have shift right, and we also have the shift left. When they are developed using the D flip-flop, this is what we have. And this is a type of shift right, where my information is moving this way. So you can see the clock is on this side, clock, and it's a common one. So my information will move from here to here, from here to here, from here to here, after every clock. Now clock comes in, what was here moves here. What was here moves here. What was here moves here. So assume I have a case of 1 here, 0, 1, 0. Tell me after the next clock what we are going to have here.
1,
1, that's correct. What do you have here?
0,
0, that's correct. What do you have here? This one moves here. This 0 moves here. This one will move here. So it's 1. What do we have here?
0.
No, we don't know. I don't care. Because information is coming from here, this way. So you can't tell what is coming from this side. It could have been 0 if you rotate. What you have just given me as the answer for 0 is when you say rotate right. If you are rotating, then this comes here. Is that okay?
Okay.
Yeah, so we also have rotate. We have shift. So, but as of now, we are talking about the shift. So, what about shift left? What do you expect? Information will move this way. So, which means the clocks will be this side. I'm not sure that it's drawn down here. No, it's not given. Yeah, it is. You have it. So please note that these are shifts left. We are moving your information this way. So that's how it appears. And you can also try with values here. You put some value here, you put another one here, and then you see what comes after next clock. I think that's all about registers. So the last section is on counters, which I will talk about within just like maybe 10, 15 minutes, 20 minutes, we'll be through. So that's the last section. So what I will advise, because we just have 1 minute, please know that I'm just putting up the link immediately. So you rejoin, just rejoin when it restarts. Just rejoin immediately. I'm not giving a break because taking a short time.